So let's go ahead and get started. I want to welcome everybody to this rapid interactive session, Thursday A02. There is another one going on, of course, in parallel with us, A01. This RI session is on control of robotic systems. And then I'm Cam Liang from the University of Utah. I'm the chair of the session. I have here with me Professor Santosh Devasya, also the chair of this session from the University of Washington. And we have our keynote speaker here, Professor Yancy Diaz-Mercado from the University of Maryland. So the way this session works is we will have first start off with a 15-minute keynote presentation. And our keynote speaker is up here as one of the panelists, and he will be able to answer questions that you pose on the Q&A feature here in real time. So he'll be able to type and respond to questions. Then after the keynote presentation, I'll stop the video and we'll take questions for about 5 minutes. And then afterwards, all of the keynote talks, I believe there are 21 or 20 actually, right after the first one, they will play back to back. And they're approximately 3 minutes long, and they should have little transitions to indicate the paper number. One thing I do want to point out though, so don't be alarmed, there is one talk that the video was not uploaded, unfortunately. And so you will see essentially just a blank screen with the paper number, and it will run for 3 minutes, just so that we can kind of stay on time. And just to give you a heads up, I believe it's paper number 5. In this batch. And so don't be alarmed. It'll sit there for 3 minutes and then we'll transition to the next paper. A couple things that's going to happen is in the chat, you're going to see links that Santosh is going to be putting up. And that is 2 things. One is for the, I guess we call it the People's Choice Award for the RRI presentation. And this is for this particular session. Go to the link and you can select your favorite, and that pool will close at noon today. And then also the second one is the Hugo Schuck Award. There's a link for that to take you there for the information and what to do. Anything else am I missing, Santosh? I think that's all the download
the videos maybe.
Yes.
It'll end by August 15th.
Yes, August 15th. So the other thing is all of these videos that have been uploaded by the authors are going to be available under the online program through Paper Plaza till August 15th. So please binge watch and download as you please. And then after that, it will close and the videos will not be available. However, the papers will be available in PDF form. Now, after this session, starting at 11 o'clock, between 11 and 11:45, all the authors of these papers that are being presented here will go to their respective Zoom links and be available to answer questions. They'll probably put up some additional slides or even put their videos back up. And then attendees can go in and interact with them up until about 11:45-ish. All right, so let's go ahead and get started. It is my pleasure to introduce to you Professor Yancy Diaz-Mercado from the University of Maryland. He is our keynote speaker for to start off this RI session. And his talk is shown here, multi-agent control using coverage over time varying domains. And I'm gonna go ahead and play the video. And please feel free to use the Q&A and he will answer them using, by typing responses. Then afterwards, we'll do a live Q&A. Hopefully you can hear everything.
Hello, and welcome to this keynote presentation for the Rapid Interactive Session on Control of Robotic Systems at the American Controls Conference 2020. I want to give a special thanks to the organizing community for allowing me this honor and privilege of presenting. My name is Yancy Diaz-Mercado. I am an assistant professor at the University of Maryland College Park in the Department of Mechanical Engineering. Today I'm going to be presenting work that has been conducted by my very talented PhD student, Xiaotian Xu, on multi-agent control using coverage over time varying domains. In our lab, we're interested in this notion of control of swarm robotic systems. We believe that there is strength in numbers and the coordination that can happen between these swarm robotic systems that can lead to many interesting challenges and different advantageous properties, such as robustness due to the redundancy that happens of having multiple units, such that if one unit fails, then the other units can pick up the slack. Complementary capabilities such as heterogeneity, task parallelization that may speed up the process. In the particular application of human-swarm interactions, this notion of hybrid intelligence, where you have human intuition and adaptation combined with the artificial intelligence from the swarm. And the challenges, very interesting challenges, like I mentioned, such as scalability, coordination among the different agents, and understanding and dealing with emerging behaviors that occur because of, for example, having multiple agents occupying a shared space. We believe there's a lot of potential for these swarm robotic systems to impact many fields, such as transportation systems, construction, assembly. In our lab, we've taken an interest in the areas of energy generation, healthcare robotics, and public health. Especially now, due to the pandemic situation that we're in, we believe that the swarm robotic systems can provide some notion of social distancing, such as last mile delivery, disinfection of highly populated areas, and symptom monitoring and tracking. In this particular work that I'm going to be presenting today, we're addressing the question of how do you manipulate a swarm of robots. And we try not to attempt to control individual robots with this work. Instead, what we're going to do is we're going to set an objective for the collective of robots. And the individual robots then coordinate their motion with one another in order to achieve this collective objective. And the way we think about this is that we're actually abstracting the swarm of robots as a mass, right? Almost like the kinetic sand that we see on the diagram here. And so even though it's composed of many particular particles, we're not trying to control these individual particles. We're grouping them together in some way in order to achieve different shapes. One approach to think about how do you control these particles is by setting a density, the density of these particles. Or in other words, you control the concentration of them inside of the domain. And in so doing, you might be able to achieve different formations like we see on the diagram here. And this is an approach that we have taken in the past. In this work, we're going to take a slightly different approach where we think about the boundary itself as the thing that we get to control. Kind of like taking the sand and then roll it up into a ball, right? And actually being able to take this ball and move it around. This is going to allow us to control the overall position and scale of the swarm. We're going to be using coverage control in order to do this, as it provides a scalable mechanism to influence the swarm of robots with these abstractions for the density and concentration of the robots and the boundary or the position and scale of it. To formalize this a little bit, the coverage control problem over time-varying domains is the one that tries to minimize this modified locational cost H, which I will explain in a moment. It's modified in the sense that we are taking a time-varying convex domain D as the domain that we are attempting to cover. Inside of this domain, we're going to be defining a time-varying density P. It maps points in the domain and time to positive numbers. The larger these positive numbers are, the more important certain points in that space are. And the more important points in the space are going to drive the robots to concentrate around those points. The objective is to minimize this cost with respect to the position of the agents. And we're going to denote Pi of t as the position of the ith robot at time t. Whenever we see a position vector P without a subscript, that means that it is the ensemble vector of stacked positions for the different agents, a long vector with all the positions. The locational cost itself accounts for the different position of the robots in the domain by partitioning this domain into regions of dominance. So what that means is that each robot is going to be in charge of their particular carved up part of the space. We're going to be using a Bornet tessellation of the domain, which is to say each agent is going to be in charge of all the points that are nearest to that robot. And the locational cost itself then becomes the summation of the area integrals over these Bornet tessellations, which are a function of the state of the agents at time, because of the time-varying domain, as weighted by this integrand that incorporates the density function inside of it. Now, in other words, the objective that we're trying to achieve is figure out what is the best configuration of agent positions in order to cover this time-varying domain with respect to some time-varying density, which we are going to think as exogenous inputs into the system, the domain and the density. Now, this locational cost is non-convex even in fairly straightforward situations where you have, for example, uniform density and a polynomial domain with few rules. And so when we try to minimize these configurations, we really think about achieving local minima or near optimal solutions. It is a well-known result that for minimizing these configurations with respect to the position of the robots is that a necessary condition for optimality is that the robots form this centroidal-Bohr tessellation configuration. So what does that mean? It means every single robot's position pi coincides with the center of mass for their respective Voronoi cells. The center of mass is provided by the expression that we see here on the slides. It's the rational expression of two area integrals, whose domain of integration is actually the Voronoi cell, state-dependent and time-dependent because of the time-varying domain. And the integrand is time-dependent through the density function. And so if we want the robots to occupy this center of mass position, that means that we're asking the robots to track this time-varying and state-dependent reference. And we want to control that it is able to achieve this. Now, intuitively, from a controls theoretic standpoint, if we're just tracking our time-varying reference, then we need a few building blocks into our controller. First one is tracking feedback. This is pretty standard. Second one is tracking feed-forward. Right? This is going to account for the time variations that we have from the domain and the density, and are going to allow us to then maintain this centroidal-Bohr excitation once we achieve it. Coordination among the agents is going to allow us to take into account the state dependency and the Bohr tessellation that affects the domain of integration in order to, again, maintain this time-varying domain and densities centroidal-Bohr tessellation. The coverage control law that we propose is given by the following expression. And it looks similar to expression that we have proposed in the past, because there are nuances that are hidden here within the different partial derivatives that are unique to the problem that we're addressing here with the time variables. But we can see that all the building blocks that we required in order to achieve this, maintain these centroidal-Bohr tessellations are present. We have a standard tracking feedback term that actually looks a lot like this standard Lloyd's algorithm that's very well used in coverage control problems. We have a feed-forward term, the partial with respect to the centroids with respect to time, that accounts for the time evolution of these domains and the densities. And we have a matrix that accounts for state dependency here and provides coordination among the different agents. In previous work, we've shown that this matrix can actually be swapped out with truncated versions of the Newman series expansion in order to set the desired level of coordination among the agents and decentralize this control law. For example, taking only the two terms in the Newman series expansion would only require coordination between the nearest neighbors in the domain. And so in the paper, we show that the control law with the updated feed-forwarding terms and expressions are still able to provide local exponential tracking of the centroidal-Bohr tessellation. To account for time-varying domains, we have the following proposition in the paper. It says that if we know the normal velocity of almost every point in the boundary of the domain, time-varying domain, then the feed-forwarding term is given by the following expression. Now, the expression itself is not so important. What is important here is that this first term accounts from the time variations from the density. The second term accounts from the time variations of the boundary of the domain. And because the domain of integration for that integral on the second term calls for the intersection of the Voronoi cell with the boundary, what this says is that only the agents that are on the explicitly sharing a boundary in the Voronoi cells with the boundary of the domain are explicitly influenced by the domain itself, being time varying. The agents on the interior are not explicitly affected by the time variations. They're implicitly affected through the coordination between the different agents. And this result follows from application of the Leibniz-Reynolds transfer theorem and a lot of algebraic manipulation. So the scalability of this coverage control scheme was addressed in the paper as well. And what we find is that under uniform density and 2D convex polygonal domains, the algorithmic complexity for our approach is actually constant in time. Here we see a simulation with 100 robots where the square domain is actually traversing a circular path. What we see here is that the agents, they end up forming this hexagonal configuration. And this follows, this is the heart of why this algorithm can actually be enacted in constant time. In the paper, we show that we can find closed form analytical expressions on the case of uniform density for every single term in the control law. And these closed form analytical expressions are going to be function of the position of the neighboring agents in the swarm. In order to find these neighboring agents, we need to construct a partial Born diagram. There exist methods that allow us to compute these on average with a time complexity that depends on the number of neighbors and the number of neighbors. Now, from computational geometry, a result from that follows from Euler's relation, we actually know that the average number of Delaunay neighbors is equal to 6 in 2D, and the number of neighbors is equal to 12. Right? Again, this is readily evident from the simulation where we see this hexagonal Voronoi cells that end up showing up, which means each agent has 6 neighbors that it needs support and needs a position. We implemented this this algorithm on a multi-robot system and constructed 2 demos. The first one I'm going to show here is defining a motion plan on the actual domain. Now, the domain is independent of the number of robots that are occupying that domain, right? So the same motion plan that we're seeing here for 3 robots is actually also used for 4 robots, 5 robots, 6 robots. Nothing changes in the implementation other than the coordination that needs to happen between the individual agents. And what we see here is that through the control law and coordinating the position with the motion from the different agents, the agents are able to reconfigure as necessary in order to maintain optimal coverage and track the time-varying domain. And in so doing, we're controlling the entire swarm of robots without having to worry about the individual robot in the space. And we managed to transport them from the left to the right while avoiding the red obstacle regions. Here we are directly projecting, I should mention, the obstacles and domain and all and everything else onto our workspace to an overhead camera. Same implementation or the same concept can be applied by, instead of using a motion plan, using human input. And so Shelton here is using his cell phone to provide a reference signal to the domain, not the robots, and control the domain's velocity. And so we asked him to move the domain from the left to the right while avoiding the red obstacle regions. Sometimes he doesn't do very well and he ends up colliding with these. And so we've infused the domain with the ability to avoid this obstacle unsafe regions. And so this brings up an interesting feature here that because the robots are always occupying the interior of the domain, it automatically provides a level of guaranteed safety for the robots, that the robots are not going to go into the unsafe areas because the domain is not allowed to go into the unsafe areas. And so to conclude, we presented a scalable algorithm for manipulating a large team of robots via coverage control over time-varying domains, provided exponential tracking results to the locally optimal configurations. We've shown that under uniform density, there are closed form expressions, which leads to a constant time implementation even for large teams of robots. And so the punchline here is that coverage domain can then, of a time-varying domain and a time-varying density can serve as exogenous inputs to manipulate the swarm into executing motion plans or incorporating human inputs. So thank you so much for watching. If you're interested in learning about this project or the other projects that we have going on, please visit our website, ccrl.edu.edu. Again, thanks for watching.
Okay, great. And everybody, I'm assuming everybody can hear me. So we're going to go ahead and turn to questions now to our keynote speaker. So Professor Diaz Mercado will take some questions here, and I think one has already been asked. So go ahead and pose your questions, and he can answer them verbally.
Should I address the question that I just answered? It was just
yeah. So you could elaborate on that if you'd like for everybody, and then we can wait to see if other questions come in.
Sure. So the question by Nicola Vezzo is this approach decentralized or centralized, and how does it scale? So there's the expression that we show with the matrix inverse is actually a centralized implementation, but we have a mechanism to find distributed approximations to that we can enforce the level of coordination that we want, nearest neighbors, 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 and so on and so forth. And we show in the paper that under uniform densities, so density is equal to 1 and not time varying, we actually have closed form analytical expressions for every quantity in terms of these neighbors. And since the number of neighbors due to geometry is limited as we pack the space with many agents to a finite number, about 17 on average, this can actually be implemented. It scales very well with the number of agents. It's constant in the number of agents, regardless of how many agents we have in the swarm. And so please go to the paper if you want to find the details. So it's pretty scalable.
So there's another question by, yeah, go ahead.
So the question by Sean Anderson, do you account for the size of the robots and thus knowing how many can be packed in the space and how many affects the innate safety guarantee? So the answer is no, we assume single integrators, so these are point particles. Now the robots lie strictly in the interior of the Borneo cells. And so you can do a very rudimentary, if you have uniform density, for example, kind of bounded space, you can kind of distribute the space uniformly and you'll find that, that what the average size is going to be for the domain required to pack all the robots inside of them. But we don't explicitly address this in this paper. No. Does that answer the question?
Okay, any other questions for our speaker? Okay, it looks like there's one more coming in, on two more, good.
Yeah, so from Sanchit Butayo, thank you for the great, you're welcome. It's one of the videos where you showed human input. Do you have thoughts on how to address erroneous inputs? So in that particular implementation, it was more of a demo that we actually have for when people come to the lab, we give them the cell phone and we allow them to play with it. So that particular implementation only allows the human to provide reference to the bot. So you can basically say unit direction that you want to move in and they'll transport the bots. We've infused the bots with the ability to avoid these obstacles. So they won't actually go into the obstacles. So if the humans, the only thing that humans can really do is go left, right, right. If they try to purposely, and many people do, to go into the boxes, the bots will just kind of stop and it won't allow the robots to go into these boxes. And we're also considering, hey, how do we take human input and then, try to implement mechanisms that will kind of infer what you're trying to do with the swarm, right, as opposed to directly input the human reference, it's specifically to account for stuff like erroneous inputs. But again, that's not something we consider in this paper in particular. And then by Demetris Coleman, could this approach be extended to consider robot dynamics for more complicated systems? There is some work that tries to address their coverage control, on the more complicated dynamics and the likes, but that's not something we're doing explicitly. We have thought about, and we have done work where we utilize coverage control notions in different more complex dynamical systems. In fact, we have a talk later today from Felipe Rivera, that's a plug, so please go and check that out later today, where we do something like that. And the idea there is basically we provide, the coverage control becomes a reference signal for the actual dynamical system. So we separate out the two and basically we do this notion of tracking that would allow us to do that.
Okay, great. Thank you for all the questions. So we're going to continue on with the rest of this session. I do want to remind everybody to vote for the People's Choice for the RI presentation for this session. The poll will close, the poll actually closed, I think at noon today. So make sure you grab the link out of the chat and do copy the link because it'll disappear once we shut down this webinar. And so let me remind everybody again, I'll be playing these 3-minute talks back to back and it'll last roughly about an hour. No questions, obviously. That's reserved for the second session from 11 to 11:45. All the authors and speakers will go to their respective Zoom rooms and answer questions and put up posters and even their current video. I do want to remind you that talk number 5 was not uploaded to the system, so thus it is blank. You'll see just a 3-minute blank screen with the paper number. All right, so I'll go ahead and start playing this.
Thank you, everybody, for attending.
Hi, I am Paul Bonchek, and I'm a PhD student at the University of Virginia in the Electrical and Computer Engineering Department, working with my PhD advisor, Nicola Bezzo. In this presentation, I will discuss our recent work titled Model-Based Randomness Monitor for Stealthy Sensor Attacks. From a CPS point of view, cyber attacks can act on different surfaces, like sensors, communication, and actuators to disrupt system behavior. In this work, we focus on sensor attacks that inject false data into measurements hiding stealthily within sensor noise, with the intent of pushing a system off its desired trajectory while being undetectable by state-of-the-art detection schemes. In particular, we note that an attack that wants to hijack or compromise an operation of a system will have to create non-random behavior and contradict a known system model. Even if it hides within the noise of a sensor, in order to perform such hijackings, an attacker will have to create non-random conditions in order to be effective. In this work, we exploit these considerations to build a monitor to search for sensor inconsistencies. Specifically, we leverage 2 tests to check for inconsistent behavior by monitoring the residual, that is the difference between measurement and the state prediction. The first monitor uses the Wilcoxon sign rank test to monitor whether the sequence of residuals are symmetrically distributed in zero mean, while the second monitor, that is a serial independence runs test, determines if the incoming residual difference sequence contains non-random patterns which may not be detectable by the Wilcoxon test alone. In this video, we are showing an example of an experiment conducted on a UGV that is tasked to perform a square trajectory, avoiding the red regions while monitoring for cyber attacks with a Wilcoxon serial independence test and a well-known bad data detector. At some point, an attack on the IMU sensor appears pushing measurements to one side and making the UGV believe that it needs to correct toward the left, thus entering that undesired red region. However, as you can note on the top graph, the Wilcoxon test in this case is able to detect non-random residual behavior, resulting in an increased alarm rate. To hear more about this work, please visit our poster. Thanks.
Hello everyone, and welcome to my presentation. My name is Harshit Kumar, and in this video, I will be talking about the navigation of quadratic potentials with star obstacles. Path planning involves 2 components: reaching a specified target goal from a start configuration and remaining in the free space or avoiding obstacles along the way. Because this is a fundamental problem in robotics and control, there exist many approaches to solve this problem. Each has their own inherent advantages and disadvantages. Our approach is informed by the artificial potential approach. Artificial potentials combine an attractive potential to the target with repulsive potentials from the obstacles. The agent follows the gradient field generated by this artificial potential to reach the target. This approach is popular as it can be implemented without global information and with smooth trajectories which are favored for bounded torque actuated robots. Unfortunately, artificial potentials are known to be incomplete, as the agent might converge to a local minimum of the potential rather than its goal. Subject to certain geometric conditions, the Riemann-Kodachek potential can be proven to have exactly one local minimum at the agent's target. Spherical obstacles satisfy these conditions, but they lead to over-conservative obstacle estimates. When the obstacle is estimated by wider shapes, such as ellipsoids, a local minimum forms adjacent to the obstacle. In previous work, we showed that a correction to the dynamics enables the agent to circumvent wide ellipsoidal obstacles. Pre-multiplying by the inverse Hessian converts the wide ellipsoid into a sphere, and the local minimum is converted into an unstable equilibrium, as shown here on the bottom right. In fact, due to the quadratic form of ellipsoidal obstacles, the proposed dynamics are simpler than they appear. A closer inspection of these simple dynamics allows us to extend these convergence results beyond ellipsoidal obstacles. Notice that x minus x star denotes the direction from the agent to the center of the quadratic potential. Similarly, x minus xi denotes the direction to the center of the obstacle. As such, we propose the same simple dynamics can be applied to a more general class of obstacles called star obstacles. Star obstacles are defined by a center point such that the line segment between the center point and any other point is contained in the obstacle. In fact, all convex obstacles are star obstacles, with any point being a center point. In this work, we proved that from any starting configuration, the agent will reach the goal without colliding with the star obstacles. Thank you for attending my presentation, and I look forward to speaking to you in detail during the interactive session.
Hello and very welcome to this short presentation on the model-based cascaded control concept for the bionic motion robot. And the bionic motion robot, which you can see on the left here, is a quasi-continuum manipulator consisting of 3 segments actuated by pneumatic bellows. So it is a pneumatically driven robot, and it is actuated by pairs of bellows. The title of the paper says, I will quickly present a model-based, so the model, cascaded control concept, so as well the control concept in very brief form in this short presentation. So starting with a basic principle how the robot works, we can see here one of the segments. On the left it is deflated, fully deflated, and on the right, here in this picture, right side of the bellows is inflated with air. And what you can see is that the air results in a pressure force, and it bends the segment. And each of the segments, as mentioned before, consists of 4 bellows, which are then actuating in an antagonistic way in order to steer the robot. And it further has a stiff backbone, which you can see kind of in the picture on the left as well, which makes the robot stiff with respect to an elongation. And it also makes the robot only a quasi-continuum manipulator because it cannot fully move free, but it has, compared to the actuator degrees of freedom, a large number of freedoms in terms of the motion. So how did we model the system? First, we have 12 bellows, which are modeled with dynamic equations for the pressurized air, which is sketched here. And second, we have used a constant curvature approach in order to derive the mechanical motion dynamics, equations of motion, which you can see on the left. And those are obtained then by the Lagrange formalism, with generalized coordinates taken as the bellows lengths. Regarding the control concept, we used a cascaded control concept with an inner pressure control loop and an outer mechanical control loop, and optionally also a force-free control was implemented, which you can find in the paper. To illustrate the damping from the mechanical control loop, you can see on the right-hand side a comparison with the purely pressure controlled, so to say, mechanical feed forward, and in gray, the position control of the system, where you can see the damping. If you're interested in more results, you can look into the paper, and we are very looking forward to the following discussions. Thank you.
Okay, so this is the talk without a video that was uploaded. And so this screen will be here for basically 3 minutes until the next video starts. I do want to remind everybody that we have the link that's posted on the chat here. If you can get access to it, that'll allow you to vote for the People's Choice Award for this RI session. And this poll, again, will close at noon today. And in the other RI sessions, we have the same thing going on. And then on Friday, we'll, by then we'll compile all the information, and during the award ceremony, we'll announce the winner of the People's Choice Award for the RI sessions. And also, there's information about the Hugo Schuck Award as well that's in the chat. So please visit those links. And again, I do want to remind all the attendees and the authors after this session the speakers will go to their respective Zoom rooms that's listed in the program, and they will continue to present their work and then allow you to attendees to enter those rooms to interact with them, to ask questions, and yeah, to get more information about their work. Three minutes seems like a long time, doesn't it? So this video should end, and then paper 2.6 should start right up.
Hello everyone, my name is Tatsuya Miyano from Toyota. This is a collaborative research with Professor Lombard and Professor Egerstedt at Georgia Tech. The title is Primary Gradient Dynamics for Cooperative Unknown Payload Manipulation without Communication. In this paper, each robot uses local measurement to decide an optimal input force so that the unknown object tracks a reference velocity. In particular, available information of each robot is very limited. They do not know their positions. They do not communicate with each other. Each robot can only obtain its own velocity and acceleration and common reference direction. We consider a payload manipulation problem where a rigid object is grasped at n+1 point by n robot and one external actor, for example, a human participant. They cooperatively transport the object. Input matrix of robot, influence of external force, and centrifugal and Coriolis term are unknown. This paper presents a novel distributed optimization algorithm based on primordial gradient dynamics. In general, we need to know the B matrix to apply the primordial gradient dynamics for this type of optimization problem. However, the cooperative payload manipulation system has a suitable relationship between global and local velocities. By virtue of this suitable property, we can obtain fully distributed optimization dynamics and an additional mild assumption of difference angular velocity. Our manipulation scheme amounts to implementing a combination of low-pass filter and PID velocity controller. As a main result, local exponential convergence of the present dynamics can be proved. Finally, we demonstrated the effectiveness of our present approach through the numerical simulation. We can confirm that the object velocity converges to the reference, even after the decrease of the number of active robots. I look forward to having an opportunity to discuss this paper with you later. Thank you very much.
Hello, everybody. My name is Hamid Farvanejad, a PhD student at Arizona State University under Dr. Espen Berman. Collective transport has potential applications in construction and assembly, in debris removal after disasters, and planetary explorations. A striking example of collective transport is what is done by ants because they do not exchange information, they have no global position information, they have no knowledge about the payload and their teammates, they are not given predefined trajectories, they have knowledge only about the direction to release, and they rely only on their local information. So we define a problem in the framework that we assume that we have differential robots with one of manipulator arms. The robots have arbitrary configuration and distribution on the payload. They have no information about the payload's dynamics, geometry, and its position and velocity. They have no knowledge about the distribution and configuration of other robots. They have no knowledge about the attachment vectors, and they have no explicit communication capabilities. And the objective is that we want the robot to transport the payload towards the goal with a desired constant velocity, and want the robots to converge to a stable steady-state configuration during the transport. To solve this problem, we first derive the equation of the holonomic constant between each robot and the payload. This holonomic constant is just this red vector, the kinematic chain here, which has this equation here. And if we get the time derivative of this equation, we'll get this Pfaffian form of the constraints. And if we integrate all these constraints for all the robots, we'll get this large equation with this large constraint matrix, the A matrix, and we know that the velocities of the entire system are restricted to evolve only in the null layers of this A matrix, which is spanned by these 4 unit vectors, and among all these, E2 has a curl, because when we want to design the desired velocity for each robot, we use just E2 to design this desired velocity. And when we design the desired manifold motion with this equation, we can prove that with this desired manifolds, all the contour objectives are entirely satisfied. And with this linear parameterization of the robots, which we can design this totally decentralized contour law and adaptive law, and we can prove that the closed-loop system is globally stable, and all the manifold parameter SIs converge to 0 with this control law. And we did a simulation in VBOT with 8 robots, and we can see that the payload here is transported to the goal with a desired constant direction without significant rotation. And here we can see that the parameters of the desired manifolds are all converging to 0 for all the robots. And we can see that the robots' speeds are converging to identical values. And here the heading angles and the angle of the manifolders are converging to stationary values for all the robots. Thank you.
Hey everyone, my name is Sriram. I'm here to present my work on target tracking with ground robots using DJPDA. Backing up a little bit, multi-target tracking is the goal of this multi-target tracking is to estimate the state of a given dynamical system. And this is usually performed in 2 steps recursively: uncertainty forecasting and information fusion. The problems with the latter step is that targets often do not voluntarily reveal their information regarding the state, and we need this information to determine which measurement to be used for which target to perform a state update. And this is complicated by the presence of clutter and is compounded by the scale of the problem. And this in general is known as the data association problem, and there are many solutions that exist for it. I'm going to be focusing on one here. To formalize this a little bit, this is the multi-target nonlinear motion model we're using in this paper. And I want to draw your attention to 3 things here. First, the number of targets, which is more than 1. The state of the object is given by a nonlinear process model. And finally, z tilde of p, which is the measurement needed to compute the state. But what we get in a practical scenario is zj of k, and we need to reconcile these two somehow, and data association is how we do it. And the way data association is performed in this particular paper is by using DJPDA, which is a tensor framework which was developed and published earlier. And I'm not going to go deep into this one, but I just wanted to mention that. And the experimental design here is by using a fleet of turtle bots. The objective of this case study was to control the complete tracking problem and to test that DJPDA framework already published to see how it fares in a real-world scenario with clutter and higher data frequency. The experiments were conducted in a gradual manner by having one agent to start with. The complexity was added by adding additional agents with the same process model and adding an undesired object with a different process model, and clutters with an unknown trajectory, and random interference by using humans. We also did some simple data cleaning for this one. we eliminated the wall noise because we knew that the wall was a known position. We also took into account the point clouds and did a k-means clustering algorithm to determine what position each point cloud represents, and that would be a turtlebot position. And I want to draw your attention to a couple of results here. First one, this is the trajectory as computed after the turtlebot measurements were received. This is using the algorithm, data association algorithm. And the two main results here are ranks versus the log time and the uncertainty. So ranks are the tuning parameter that tensor framework introduces. The higher the rank, the higher the complexity of the underlying algorithm. JPD is known to be exponential. The key thing here is that ranks curbs that exponentiality by introducing a tuning parameter. Once a rank is set, that time is also set. And the uncertainty reduces the number of ranks. And this together would give us an additional tuning parameter. That would be all for now. Thank you.
Welcome everyone, my name is Gene Chagas-Fass. Today I'm going to be presenting my research, which is expanding humanoids' material handling capabilities using capture point walking. Alright, so first let's define material handling, which is the use of manual, semi-automatically, and automatic equipment to transport, store, and handle various materials. To successfully assist humanoids should be able to interact with use of common materials, moving equipment such as carts, dollies, wheelbarrows, and that's what we're going to be focusing on here. There are a lot of applications within disaster cleanup, agriculture. We will be using the DRC Hubo robot, which was developed during the DARPA Robotics Challenge. So the first thing we got to consider when we're talking about pushing a cart is the external forces. And for the walking pattern, we have chosen capture point. Now, if you take a look at equation number 1, you will see that this resembles the classical inverted pendulum equation, and that is the approach we've used to model our capture point methodology within the inverted pendulum theory. I have validated the methodology on MATLAB, and you can see that the center position in X is indeed cutting right in the middle of the reference ZMP. Here I have a little bit of the system integration. DRCU was equipped with 4-stroke sensors on the ankles and wrists, and Poto is just the overall software that communicates between those sensors. By observing humans pushing carts, we've noticed that arm compliance is quite of a must if you ought to have the robot to push the cart and walk at the same time. So for that reason, we have then applied a arm compliance based on friction. And to solve that problem, we had to ensure the desired wrist position to the high dimension nonlinear robot's arm, and we just use a traditional feedback linearization based technique. The robot is capable to keep stable walking even though the cart is constantly shifting its center of mass. And you can also observe the arms are indeed using the friction compliance to pushing this cart. This is one of the carts that we used. There was another cart where the handle is 90 degrees and upwards, and we're going to be showing right here. The capture point pattern, it stables itself as the walk goes, as you can see on the overall plot. Same thing can be seen on the YZMP. The takeaway from all of this is that cart pushing and material handling remain an open problem. The robot-object interaction easily destabilized walking. So this problem has to be solved before humanoids are deployed in distribution centers, disaster cleanups. And we have successfully demonstrated capture point walking with arm friction compliance. So the next logical step is a whole body coordination, and that is coming up soon.
Hello, I am Ryan Kraus, and I am really interested in low-cost, real-time feedback control experiments. That has led me to publish some previous work on using Arduinos for real-time feedback control. But I also really love Python and would love to be able to use it in real time to do my control law calculations. I think it gives me a lot of power and flexibility. The primary challenge that I run into is that hardware that runs Python does not generally do real-time stuff very well. So in my previous work, this has looked like an Arduino connected to a laptop, and the laptop is doing the control law calculations and sending information to and from an Arduino over USB. And then the Arduino controls the timing and interacts with the plant and reads the sensors and sends the actuator commands using digital to analog conversion. In this work, we're switching from a laptop to a Raspberry Pi, and we're switching from serial to I2C as a way to reduce latency. Previous work, Python essentially sits waiting for a response from Arduino. As soon as it gets the sensor values, it does its control law calculations and sends out a new set of commands. The Arduino waits for a timer interrupt, sends those commands to the plant, and then sends data back to Python. And the primary bottleneck in this situation is how long it takes from the time the Arduino sends sensor information until the time when it receives the next batch of actuator commands. And that latency can average 3-ish milliseconds and be as high as 5 or even slightly over 5. And so that bottleneck limits this approach to roughly a 200 hertz digital control frequency. So reducing that latency was the primary goal of this work. And it just basically came down to serial has latency that I don't seem to be able to get rid of. So switching over to I2C and using 2 different Arduinos allowed Python to ask the timing Arduino when the next timer interrupt event occurs, and then this communication cycle, we're essentially doing the same things, but doing it over I2C has much less latency than the serial-based approach. Using pin toggles from the Arduino combined with an oscilloscope, we want to measure the latency of this approach in the same way we had done with the USB serial approach, and we find that we've reduced that latency with this approach by roughly a factor of 3, which should make it possible to do real-time feedback control experiments using Arduino plus Raspberry Pi at roughly 500 to 800 hertz.
Hello, my name is Sean Bredin, and I'm pleased to present this paper, Energy-Aware Path Planning for Skid-Steer Robots Operating on Hilly Terrain. The lead author of the paper is the recently graduated master's student, Veronica Grunge, and my co-authors are Jesse Penser and Carl Reichert. The problem we are seeking to solve in this work is represented by the human challenge of climbing a mountain. The minimum distance path is a straight line toward the peak, whereas the minimum energy path is often complex, longer in distance, and generally seeks to minimize changes in elevation. While minimizing distances from a start to end point is a relatively trivial task of connecting straight line segments, the calculation of minimal energy paths is made difficult for off-road skid steer vehicles due to the calculation of slope energy and spin-in-place energy in the presence of deformable or slipping soil surfaces. Prior work by the authors shows the means of modifying the two-wheel unicycle robot dynamics to include skid steering effects. These dynamics are based on the instantaneous centers of rotation rather than the center of the tire or treads. This modification allows straightforward modeling as well as online estimation of energy utilization of skid steering and grade climbing on deformable soils. The problem of finding the minimum energy trajectory in a hilly terrain is a non-convex problem, particularly with changing soil frictions. To obtain solutions, this work uses the sampling-based model predictive optimization, or SBMPO algorithm, with models of terrain topology and soil parameters to develop energy-aware path plans. 2 situations were analyzed that prioritize either distance or energy for path planning on a simple simulated hill topology with varying realistic friction parameters. These represent soft or hard soils. The parameters for these situations are given in the table. The results show that by using homogeneous soil navigation with energy constraints, this predicts paths that follow ridge contours, whereas straight paths are preferred if the soil types are improving energy costs. In the homogeneous soil case, we observed a 10% decrease in energy, but with a 17% increase in the distance versus straight line driving. In the changing soil case, we observed a 5% decrease in energy, but with an 11% increase in distance versus straight line driving. In conclusion, the energy savings were generally less than 10%, with a trade-off of increasing the distance by a percentage factor of 1.5 to 2 times more. Future work includes more aggressive topologies, speeding up the algorithm, which is currently not real-time, and experimental testing of the algorithm with real robots. If you have questions, I'd be glad to discuss in the breakout session, or you can email me, Sean Brennan, at this address.
Hello everyone, my name is Yuan Gao. I'm a PhD student from the Trace Lab at the University of Massachusetts Lowell. In this presentation, I will talk about our research on impact-aware online motion planning for fully accurate bipedal robotic walking. This work is done with Dr. Shinya Da from NVIDIA and my advisor, Dr. Yan Gu. Real-world operations in complex, dynamic environments demand online planning. However, the computational burden of the associated walking motion generation is heavy because first, walking is naturally a hybrid dynamic process involving nonlinear state-triggered impact dynamics, and second, a walking robot typically has many joints causing a high dimensionality of the robot's state space. Therefore, realizing online impact-aware planning for like robots remains a challenging problem. The objective of this work is to develop an impact-aware planning method that generates a desired full-body motion profile in real time for fully actuated walking robots. Our proposed planning method reduces the computational burden of planning by constructing a keyframe posture library offline. Also, it guarantees that the planned motion respects the robot's landing impact dynamics by explicitly considering the impact behavior. The flowchart illustrates the proposed planning method, which consists of 4 steps. The first step is to construct a keyframe posture library. A keyframe posture is a pre-computed kinematic feasible configuration of a walking robot when the foot lands on the ground. The posture highlighted in the red dashed circles are keyframe postures. A keyframe posture library is a collection of keyframe postures. The second step of a proposed planning procedure is posture interpolation, which obtains a posture that exactly fits the given footstep. Specifically, we first search for 2 closest keyframe postures, then we obtain the average posture and use it as the initial guess to obtain the interpolated keyframe posture. The third step is the velocity assignment, which is the key step to enable our planner to generate full-body motions that respect the robot's impact dynamics. At this step, we assign the desired generalized velocity to the interpolated posture obtained from previous step. In the last step, the planner generates a full-body motion based on the keyframe posture and its corresponding velocities. We have validated our impact-aware online planning method through MATLAB and Weber simulation of Darwin OB3 robot. The robot has 20 joints. Our planner is able to generate impact-aware motion of 1 walking step within 0.6 seconds. In these simulations, the nominal step duration is about 0.8 seconds. Both simulation results demonstrate the effectiveness of our proposed planner in generating impact-aware motion in real time. Thank you. I'd be happy to take any questions during the post-session.
My name is Antonio Loria. I am with the CNRS France, and I will speak about the decentralized partial consensus controller for non-autonomous vehicles over networks with interconnecting delays. This is a joint work with Mohamed Maghenem from University of California, Emmanuel Nuño from University of Guadalajara, Mexico, and Elena Panteley from CNRS France. Partial consensus control pertains to the case in which we have a group of robots that are initially far apart, and we want them to converge to a rendezvous point that is not specified a priori. In doing so, the robots also have to acquire a formation, a geometric pattern, and a desired predefined orientation. Only orientation is predefined. We address this problem under the realistic scenario in which the robots, as I said, are initially far apart, so proximity sensors are inefficient, and instead the robots use GPS measurements, and they transmit these measurements over a network, a wireless network. Now, this network is supposed to have at least 1 spanning tree so that every robot receives the information from at least a sufficient set of neighbors. And also because the network is supposed to be wireless, it induces these continuous time-varying bounded delays. The controller to solve this problem is given by these 2 equations, one for in the translation motion and another one for the orientational motion. As you can see, the controller contains proportional errors to the consensus errors that we see here. So these are the states of the ith agent, the actual agent, and these are the states of the neighbor that are received with time-varying delays. And another term that is crucial in the controller is this one here, which is the product of one function that depends only on time. It's an external function, And this function is supposed to be persistently exciting. So it can be a periodic function, or it can be just some random noise, or any other function that is persistently exciting. And the second term is this one here, which is basically some kind of norm, except that it's in a vector form of the error. So what this term is doing is that it excites the system dynamics as long as the consensus errors are delta away from the origin. Our main result is to establish uniform global asymptotic stability, and this is very important. This is very different from the literature in which usually only convergence is established. We also provide an illustrative example of 4 robots communicating in this loop fashion with random delays, and you can see that all the robots converge to the consensus point. I will leave you with these references to prove further.
Hello, I'm Evan Krell, presenting Game Theoretic Potential Field for Autonomous Water Surface Vehicle Navigation using weather forecasts. Instead of shortest distance, marine path planning is often based on energy efficiency, such as the impact of water currents along the path. These velocities may be obtained from water current forecasts, but are only uncertain predictions. We are using a game theory approach to handling this uncertainty. The boat and weather are said to be opponents in a game where the boat wants to minimize energy expenditure, and the weather wants to maximize it. Of course, the weather has no opinion, but the model promotes worst-case planning. Consider the naive boat on the left. It sees an opportunity to make a longer path that lets it ride currents toward the goal. However, the bottom image shows the actual currents, which varied enough to make the boat regret its plan. The strategic boat on the right also has the predictions, but uses game theory to determine the worst case. It finds that the shorter path is more reliable, if over-conservative, and does not regret its plan. The major contribution is robust planning with online weather forecasts. Dynamic programming is used to generate a policy across the entire planning region, and game theory is used to determine the actions of the players at each decision. Dynamic programming theoretically requires a vast number of iterations, but we are interested in the convergence rate and how many iterations are actually needed for a useful real-world policy. Here's a quick look at the dynamic programming. We start from the goal and solve it bottom up so that even the first iteration has a feasible solution. Here we see that the first iteration has actions that go directly against the strong current shown in red. In the second, some of those cells can now see that there is a lower cost route by going around the island. The uncertainty is addressed by solving a zero-sum two-player game at each cell. Here, the vehicle is shown with having the actions up, down, left, right, and halt, but the actual code uses 16 angles. The game's minimax solution describes the action for both players, and the cost for the robot to traverse that cell, assuming that all future actions follow the current policy. Here is the result using data from Boston Harbor with water current forecasts shown as white arrows. The motion plan was generated after only 20 iterations and already displays energy efficient strategies. There's a narrow valley between the strongest opposing currents that the path cuts through. But how exactly does the game theory compare to assuming static currents? Here we see a zoomed in segment with and without game theory. The one labeled DP assumed static currents, and DPGT assumed worst case with an error margin of 0.1%. 15% work is saved if the worst case were to occur. However, these models tend to have sparsely published error reports, so the error margin is synthetic here. Raising it, game theory becomes arbitrarily better. So we want to learn an estimate of the uncertainty with the boat, who then becomes a local domain expert over its lifetime of missions. Game theory allows planning for worst-case weather, and the convergence suggests useful plans from few iterations. However, we are also interested in applying approximate dynamic programming and focused Markov decision process techniques for getting plans without searching the entire space. Thank you very much.
Hello everyone, my name is MT Nuradum Tony. I'm a graduate student of University of Texas Rio Grande Valley. I've worked with my supervisor, Dr. Wendy Dong. For this paper, the title of our paper is Distributed Command Filtered Robot Tracking Control of Web Adaptive Modular Vessel with Uncertainty. First of all, we have considered M+1 web adaptive modular vessels. The kinematics and the dynamics of the vehicles are given through equation 1 to 6. In these equations, you can see small mij, which is the inertia of the vehicles, small dij, which is considered as damping, and capital Dij, which is the disturbance. These are unknown. The 0 WMP is the leader, whereas the other WMPs are the followers. The communication between the WMP is described by a diagram G. It is considered a desired geometric pattern. It is defined by constant vectors. So the formation control problem is to design distributed control laws so that the equation 7 to 9, which is described, is satisfied. So we propose to distributed controllers through backstabbing technique by equation 10 to 12. In these equations, we can see there are some derivative terms present, M3 and M5. So these derivative terms makes the implementation of the controllers complicated. So in order to remove the derivative terms, we propose distributed command filter controllers through equation 14 to 19 and through compensated signals 20 to 22. Through these equations, we propose two distributed command filter controllers FR and FL, which makes the computation really easy and also removes the derivative terms from the signals. In the graphical representation section, we consider one follow leader vehicle and three follower vehicles. The representation and the formation of the follower vehicles are shown in figure 1. The figure 2 shows the communication directed graph. The simulation results are performed in order to verify our proposed control laws. The simulation results in figure 3 and 4 shows that the vehicles follow and converge to our desired formation. So the conclusion. In this paper, we considered formation control law of multiple uncertain WAMPs and related WAMP. If inertia parameters are not exactly known, distributed robust tracking laws were proposed. To reduce the computational load in controller design, distributed command filter controllers were proposed. Simulation results show the effectiveness of the proposed results. Thanks a lot for hearing me out.
Hi, I am Lasita. This paper presents an experimental investigation of bilateral teleoperation of soft robots under piecewise constant curvature hypothesis. Soft robots are continuously deformable robots that are hyper-redundant and are fabricated using compliant material. The interest in soft robots has been due to their unique properties which could be used for safe operation in various applications. Despite being challenging, the researchers have proposed several reduced order models as well as some infinite dimensional models for these robots. Although soft robot control has expanded recently, bilateral teleoperation of soft robotic systems hasn't been addressed much. Thus, in this paper, we will exploit the soft robot's capabilities for dexterous manipulation through teleoperation using a rigid master manipulator and a soft slave robot. The dynamics of the rigid robot is obtained using the usual Euler-Lagrange form. For the soft robot, we will use the recently developed augmented formulation. Here, the robot is assumed to be PCC and the dynamics are obtained in the familiar Euler-Lagrange form. However, there could be uncertainties in the parameters due to various reasons. Thus, the proposed control framework will be designed to mitigate such uncertainties. Therefore, we choose an adaptive control framework. The control objective is to track the robot tip positions. To this end, the control inputs are computed for both the robots. Also, null space velocity of the soft robot is utilized to achieve subtasks. The experimental setup consisted of a pneumatically actuated pleated-type soft robot with 3 segments, a motion capture system, and a laptop to run the control algorithms. Due to the unavailability of a suitable rigid master manipulator, it was simulated. In the first experiment, the soft slave robot could move freely and the subtask of conforming to curvature limits was considered. The plots indicate satisfactory performance in trajectory tracking. Also, with the subtask, it is clearly seen from the photos that the configuration of the soft robot is controlled to be within the curvature limits. In the second experiment, an obstacle was set. The results illustrate that when the soft robot is in contact with the obstacle, the environmental forces are felt at the master side. Among the important insights, it was observed that the slow movement of the soft robot negatively impacted the performance of the teleoperation. This might have been due to the nature of the pneumatic actuation or due to the hysteresis. Excess input signals were observed due to local singularities. Also, although the stiffness and damping of the soft robot were considered constant, they might have been varying. Thank you, and please reach out for any questions or comments.
Researchers working on electric robots are interested in the locomotion of animals and humans, and we try to build robots that are dexterous like them. So we want to know, how can the legs store energy such that a robot can bounce and run? And we also want to know, with a simple model, how can we design a robust feedback control such that a robot can hop to the desired height with expected converging rate? Here we consider only the vertical motion because we only focus on the energy stored in the leg in terms of elastic energy. We divide the hopping system into stance phase and flight phase. In stance phase, we use a spring mass stable system to represent the electric system, while in flight phase we use a free-falling mass to represent the system. In stance phase, we can describe the simple spring mass stable system with a standard second-order differential equation as shown. With some substitutions and rearrangements, we can represent the system in a matrix form, in which the state vector x1, x2 contains the height and the velocity of the mass. When we compute the time derivative of the two norm of the state vector, we can observe the decrease in magnitude in time without control, and the state vector will eventually be attracted to the origin. We try to use a controller that can regulate the two norm of the state vector such that the state vector will converge to the desired circle and hence the desired hopping height. The two figures show the simulations of inward and outward convergence to the limit cycle. The first simulation shows the mass converges to the desired height from a high altitude. This state space plot shows that the state vector converges to the desired limit cycle, which is in red dotted line, once it enters the stance phase. The second simulation shows the mass converges to the desired height from a low altitude. Below, I am going to show some experimental results of the implementation of this controller. Firstly, we tried it on a hard contact surface. We can see the system converges to different height quickly. Secondly, we tried it on a soft form block. With model uncertainty, the system was still able to converge to the desired height. In summary, the controller is effective in controlling the hopping height with a fast converging rate, and the controller is effective even if the system is not perfectly matching the model. See you in the poster section if you want to know more detail of our research or our lab. Thank you.
Hello, my name is Andreas Papadimitriou, and I will present the work of our group with the title Experimental Evaluation of an Explicit Model Predictive Controller for an Adhesion Vortex Actuated Climbing Robot. In an effort to enable the autonomous inspection of climbing robots, the Combinova project proposes a novel climbing robot for the inspection of aeroplane composite fuselages. The robot is differentially steered with the ability to remain attached on non-ferrous and ferrous surfaces under any orientation. The platform can generate up to 7 kg of force, enabling the ability of carrying multiple tools for inspection and repair purposes. The robot is able to translate to both curved and flat surfaces and weighs approximately 1.7 kilograms. In addition, it is able to provide smooth and accurate motion performance and has the ability to translate over the different curvatures of the aeroplane, while utilizing multiple sensors for the motion of the vehicle and sensing of the generated force. This opens new ways for autonomous aircraft inspection and repair. Through the various ways to achieve adhesion, this project focuses on negative pressure vortex adhesion generation, utilizing an electric ducted fan known as EDF. The difference in pressure under the cavity of the EDF and its surroundings will induce an adhesion force onto the target surface. There are many variables that affect the maximum generated force, such as the size of the shroud and its distance from the target surface. noise, and nonlinear characteristics such as hysteresis make the adhesion control a challenging task. To tackle the identification challenge due to the high complexity of the vortex aerodynamic effects, an Armax identification is selected for the modeling of the vortex actuation system. To successfully control the adhesion performance of the robot, an explicit model predictive controller has been designed and depicted in the adhesion control scheme. The reference force is calculated from the multiplication of the gain k and the critical adhesion from the geometrical model based on the orientation of the robot in space. The EMPC gives the optimal thrust input based on the current stage of the system, while the measured force from the sensor is translated to the generated adhesion force with the use of the robot's orientation. The EMPC solves offline the following optimization problem subject to input, output, and rate constraints. Thank you for your attention.
Hi, I'm Jessica Liu. Today I'll be presenting our work titled Safe and Coordinated Hierarchical Receding Horizon Control for Mobile Manipulators. We focus on industrial settings, and the goal is to develop a motion strategy for mobile manipulators to improve the performance of a smart factory where humans and robots work together. There are two main challenges. One is that we need to solve a high-dimensional non-convex planning problem in real time. The other is that the robot needs to be able to deal with fast changes in the dynamic environment. In this work, we solved the planning problem in a sequential convex programming manner. Here, we introduce the formulation of the convex subproblem. Denote the planning horizon as H. We want to solve a control input sequence UK and result in output sequence zk plus 1. Given the current state zk, we construct the quadratic cost. We also introduce the slack variable sk to relax the environmental constraints. The overall optimization problem is as follows. Let's take a closer look on the constraints. Given the obstacle's location, the function phi I measures the distance between the robot link and the obstacle. By linearizing the function, we can construct the convex environmental constraint. We implement the motion planning module in a receding horizon control framework. The video shows that the robot can successfully avoid obstacles while reaching the goal. To deal with dynamic obstacles, we introduce the hierarchical receding horizon control HRHC that combines the previous planning module with a safety controller that runs in a higher frequency. The safety controller reacts to rapid changes and projects the input from the motion planning module to a safe region. In the video, the human worker causes a sudden change in the environment. The safe controller reacts first, followed by the efficiency controller. In conclusion, HRHC enables the mobile manipulator to perform collision avoidance while completing its task successfully in both static and dynamic environments. Thank you for listening.
Good morning to you. I am Rishik Mishra and I am affiliated to the German Aerospace Center. My co-authors and I pursue our research in orbital robotics, and in this paper we propose a novel controller design for a fully actuated robotic capture of a tumbling target. The scenario that we address consists of two agents. On the left-hand side is the target satellite, which is non-cooperative and has a multi-axial tumbling velocity. On the right-hand side is the servicer, which is a manipulator-equipped spacecraft, and we consider a fully actuated system here. The scope of this paper is the approach phase of missions concerning active debris removal and on-orbit servicing. In this phase, the servicer spacecraft has to synchronize with the tumbling target while the manipulator approaches to grasp a point on the target satellite. From a control design perspective, we see that the reference frames on the target satellite are time varying, and yet the target state feedback on the servicer is limited to only a pose feedback sensor, example a camera and its image processing. To address the issue of lack of velocity feedback, we propose the following architecture. Firstly, note that the camera measurements capture the relative dynamics between the target and the servicer. In the paper, we propose a novel extended Kalman filter which uses the target model to estimate its motion states, specifically velocity and acceleration. The filter states include the SE3 pose for the target configuration and its velocity twist. The estimated quantities are fed as both feedback and feed-forward terms to a nonlinear tracking PD plus controller. Both the observer and the controller describe the corresponding configurations as SE3 group entities in contrast to Euclidean coordinates. In the paper, we show the limitations of a conventional controller, like noise sensitivity and steady-state errors of both spacecraft and end effector of the servicer. Here we illustrate the results of only the proposed method. Firstly, we demonstrate the observer convergence using the angular velocity estimate of the target on the top right. Since the EKF also provides a filtered pose, this is used in the feedback controller instead of the noisy camera pose. A novel stabilizing term was introduced in the EKF which provides a narrow limit set of the solution. At 5 seconds, the controller was engaged and the approach phase commenced. Note on the left of the video, the end effector has very low steady-state errors. This is achieved due to the velocity feedback in the control loop. In particular, the errors are also shown in form of position errors on the top right, which is less than 1 centimeter in all components. The lack of velocity feedback may be compensated with high control gains, however this will increase noise sensitivity. Due to the feed-forward terms, the servicer spacecraft performs synchronous flight relative to the target. By doing this, the manipulator remains closer to the preferred configuration than if it were to compensate for the spacecraft errors. Therefore, we validated the effectiveness of the proposed method through simulation results.
Hello everyone, my name is Jamie from UT Austin. My presentation today will be on reachability-based trajectory optimization for robotic systems, especially given context sequences. When we control the complex robotic systems like a humanoid robot, we have to consider multiple issues. First, full body dynamics is nonlinear. Sometimes we use linear inverted pendulum model for the planning. Second, most of robots have physical joint position, velocity, and torque constraint. Third, we consider kinematic constraint for the contact and friction ratio constraint. We focus on the discrepancy between the planning and control models. For the local manipulation, we plan the central mass trajectory and full location with the TBR planner. However, we don't know the planned result can be reproducible by full-body robot due to the constraint. So we proposed a method to check the planned full location is reachable or not, and to optimize the trajectory for the whole body controller. In our previous work, we just planned the central mass trajectory and full location using TBR planner and generate swing foot trajectory using smooth interpolation like a B-spline or cubic spline. And trajectories of central mass and foot are controlled by whole body controller. However, this paper proposes an additional part consisting of kinematic feasibility test, reachability analysis, and optimal control for modifying the trajectory. Also, we propose method for obtaining forward and backward reachable sets in terms of the given contact mode. These methods are based on the sample-wise optimization. For computing the forward reachable set, we draw random input samples satisfying the input constraint and solve the QP to obtain the joint acceleration. The initial state is propagated forward using this solution. Also, we can obtain the backward reachable set by drawing joint velocity samples satisfying the constraint. Then, we check there is a pair of input and contact force in the optimization problem. If yes, we can propagate the state backward. Otherwise, we discard this sample. Based on the computed reachable set, we can test our states are reachable or not over a finite time horizon. Then we solve the formulated optimal control problem to generate a trajectory to change the contact mode. As a result, we can modify our foot trajectories for the whole body controller. These are numerical simulation results. We employ the same TBR planner and the same whole body controller. Without the proposed method, the TBR planner produces the diverging full location. However, the proposed method can make more stable walking due to the optimized trajectory. Let me briefly sum up the main contributions here. Thank you.
Okay, that concludes all the presentations for this rapid interactive session on control of robotic systems. I want to encourage everybody to attend the session that follows right after this from 11 to 11:45, where all the speakers that have just presented will be in their Zoom rooms to answer questions and participate through the interactive session. And then also, as a reminder, please vote for the People's Choice RFI presentation, and the link should be provided there in the chat box. Make sure you copy it, because once we close the session, those links will go. And again, thank you very much, and we do thank our keynote speaker, Professor Diaz Mercado, for being here, and have a wonderful time the rest of the conference. Bye-bye.